Good morning, everyone. We will begin the last day of the APC Winter School. The speaker is Raghu Mahajan, who will teach the last lecture of the black hole information paradox. And all the slides and the material will be uploaded in the website. Also, this whole lectures will be uploaded in the YouTube channel of the APCTP. You can search it in the YouTube. And I would like to thank all the lecturer, especially Raghu Mahajan, and also all the audience. Yeah, please start. Thank you.
Okay, thank you. Thanks, Youngi. Yeah, it's been a fun 3 days, and today we will discuss some more detailed properties of the locations of the quantum extremal surface, and also preview a derivation of where they come from. Okay, so the basic idea is last time people were asking a question, when is the quantum extremal surface in front of the horizon, or when is it behind the horizon? What are the kind of general conditions we can put on the location? So the most general condition like that is the quantum focusing conjecture. And this is a generalization of the Raychaudhuri equation in just classical GR. So instead of describing what the Raychaudhuri equation is, I will just explain it in the 2D dilaton gravity that we have been working with. Sorry, guys, give me one minute. Hold on. Sorry. Okay, sorry, it's just my wife also has a call at the same time, and we'll try to wrap up soon. Okay. Sorry, so we had this equation of motion, GAB phi plus GAB grad square phi minus grad A grad B phi equals 8 pi G TAB. Usually we were setting the right-hand side to 0, but now we have this more general equation. So this is the analog of in higher dimensions when we write GAB is 8 pi G times TAB. Okay. So this we don't need. And the metric we work with only has a plus minus component. So we see that these terms that are depend on GAB will vanish if we look at the plus plus component or the minus minus component of this equation. So these two terms will not contribute because G plus plus and G minus minus are 0. So looking at the plus plus component, we get the equation minus grad plus square phi equals 8 pi G T plus plus. Okay, so it's some simple equation. Now, if this is just some classical field theory, we know that almost all reasonable matter satisfies the null energy condition. And the null energy condition says that T plus plus is positive. So what we learned from this is grad plus square of phi is negative. Okay, and remember that phi in this theory was a substitute for area. And so this is the basis for proving, the area increase theorem that Hawking proved, and so on and so forth. Because so in higher dimensions, you would have that del plus squared of some area is negative. But this is the form of the equation. So we can call this the classical focusing equation. Okay, and fine. But in quantum mechanics, the null energy condition is violated. Is not positive, and in fact, it can be negative. So this condition no longer holds. Yeah. In particular, if we have an evaporating black hole, an important case of these energies being negative is the black hole horizon shrinks precisely because there is flux of negative energy going into the black hole. So it's very important for black hole evaporation that T++ not be positive. So, okay, so we can ask what replaces this classical focusing equation. So there is a conjecture which says we should replace the area by the generalized entropy. And the claim is that grad plus squared of S gen should be negative. This is a claim. And this is called the quantum focusing conjecture.
I have a question here.
Yes, please.
So,
yeah.
Usually, you hear the classical focusing equation use this null energy condition classical.
Yep.
And usually in quantum level, people talk about the average null energy condition.
Yeah,
so,
I'm going to mention that in a bit. Yeah.
Oh, okay. Okay, I will write
it. Yeah. Exactly. So we can say that maybe, Ryuta-Kenagi has the area functional in it, and its quantum uplift is we say that area should get replaced by generalized entropies. So perhaps this equation has a chance of being correct. But let's see what it implies for the stress tensor. So the null energy condition is T++ is positive, right? What the grad plus square of S gen less than or equal to 0 replaces it by is that T++ times 2 pi is actually greater than or equal to minus grad plus square of S matter. Or actually just the no minus sign here, just this thing. Okay, so this is also a conjecture. Notice that this equation is purely a field theory conjecture. It says that in quantum mechanics, even though T++ may not be positive, it cannot be arbitrarily negative. And so this quantity is not positive, it can be negative, but it does put a lower bound on the energy. Okay, and we can see how then equation 1 relates to equation 2, because grad plus square of S gen is grad plus square of phi over 4g plus grad plus square of S matter, right? Just because S gen is phi over 4g plus S matter. And on the first term, we can use the equation of motion. If we are in semi-classical theory, the equation of motion is still correct. And so we get 2 pi T++ plus grad plus square of S matter. There's a minus sign here. So there's a minus sign here. And since T++ had a lower bound, which was precisely this quantity, we get that this is negative, right? So this equation 2 is sometimes called the quantum null energy condition. Okay, so it places a lower bound on t++, which is t++ times 2 pi bigger than or equal to grad plus square of S matter. And what Jungi was asking about is the average null energy condition, which is an integral of this. So if we integrate this equation right here, integral t++ dx plus, the right-hand side is a total derivative. So if we assume that the quantity goes to 0 at the ends of the integration regime, this is positive. So the quantum null energy condition is a stronger condition than the average null energy condition. And for flat space, this was proven recently, well, a couple of years ago by Sihan and Faulkner, Tom Faulkner. Right. So the idea is that uplift of the null energy condition to the quantum null energy condition includes this S matter piece on the right-hand side. And that allows us to generalize the classical focusing equation in the box here with the quantum focusing equation. And this is a fruitful research idea where the group at Berkeley, especially with Busso and Aaron Wall, they took a bunch of classical statements in GR, which involve the area, and replaced them with the generalized entropy, and you get some true results. And this is sort of maybe the most sophisticated of those results, replacing areas by generalized entropies. Okay, Jungi, does that answer your question?
Yeah, that answers my question, but I have another question. Like,
yeah,
this you have S matter and the S generalized entropy.
yeah,
They would be not. It's not local quantity. It's
exactly.
kind of integral.
Yes.
So but the T++ is like local, like a density. So
yeah.
how this inequality work or derivative?
It's true. So it's true what you said, that the right-hand side is non-local, but that's the best we can do, and this is still correct. So what happens is usually we have some space, right? And let's say we cut it in half. And we are interested in the entanglement properties of the right-hand side, let's say, right? So usually we move this, we can think of moving this point P here along the null direction, along the plus direction. So what this grad plus square of S matter is basically moving one endpoint of the interval of the region you're considering along a light cone direction. So at a later point, you're taking the entropy of this region. At a later time, you're taking the entropy of this region. So this derivative here means moving the endpoint of your interval, like this.
I see. Also, generalized entropy is also the same.
Sorry?
Thing. I mean, the generalized entropy is also X appear as like a boundary point.
Exactly. So when I write here d plus square of S gen is negative, what this derivative refers to is moving the endpoint of the interval along the plus light cone direction.
Okay, thank you very much.
Yeah. Okay. All right, so we will see how we can use this to give us some results. But first, I should say that actually in 2D, this is just a curiosity, we don't need it. There's actually a stronger form of QNEC. Is conjectured. We can call it the conformal QNEC if we want. And that says that T++ is not just bigger equal to grad plus square of S matter, but it's bigger than that plus a positive term, like this. Okay, and why is this combination? So first we can check that for interval in flat space, the right-hand side is 0. Why? Because we have this expression c over 6 log of delta x plus. So, when we take the first derivative square, we get 6 over c times c over 6 delta x plus whole square. And the second derivative is negative c over 6 delta x plus square. So it's 0. And of course, in flat space at 0 temperature, t plus plus is also 0. So this inequality is saturated. What's also special about this inequality is that the left and right hand sides transform the same way under Weil transformations. Transform the same under Weil. Okay. And yeah, so one can ask, so even though Faulkner and Seehan proved the weaker version of the QNEC, the stronger version is unproven. There is no proof of the stronger version of this QNEC. And T++ changes under Weil transformations because of the conformal anomaly. And the right-hand side changes because S matter had this negative C over 6 log omega that we have been talking about throughout these lectures. So both of them have some dependence on the Weil factor omega, and it's exactly the same. So this is a natural inequality to write down. Okay.
Can I ask?
Yes.
So
Yeah.
this conformal. So you're saying that Faulkner and Seehan have not proved the conformal quantum null energy.
Yes. Yes.
And it's not special to two dimensions, is it?
It is. It is special to 2D because what would C mean in higher dimension? Yeah. So if you use their proof in 2D, it doesn't prove this conformal QNEC. It only proves the QNEC.
I see. So this is still open. Good. Okay.
It's an open problem, and it's only in 2D. In higher dimensions, I don't think such extra terms are known on the right-hand side.
Mm-hmm. Okay.
Just because in 2D, this combination is natural because it fixes the dependence on the metric on both sides, on omega, right? The omega is the only part of the metric. So it's simple to write down this term.
Okay, thanks.
Okay, all right. So now let's see how or what kind of uses we put it to. So first, let's see an application of Hawking's. How does Hawking prove the area increase theorem? This will be a sketch. So this is a theorem in classical GR. So no quantum effects. And it says that if you have some time-dependent stuff happening, black holes merging, etc., that the area of the horizon can only go up. So why is that? So imagine that anything collision that was going to happen has already happened. You had some stuff colliding, time-dependent stuff, but in the end, you get some stable, stationary black hole. Okay, so in the end, we have some horizon here. This is stationary, and in the past, there might have been stuff going through, blah, blah, we don't care. Point is, let's look at this part of the horizon here. Here, the area has become stationary. So d plus of the area is 0 at this point. The area is no longer increasing, right? But the focusing theorem tells us that the derivative of d plus a, I'm going to put a prime here, it just means d plus is negative. So using these two facts, we conclude that d plus of a at this point must have been positive, right? Because it has to go to 0 in the future, and its derivative is negative, so it must have been positive in the past. And that's basically the area increase theorem in classical GR. We use the fact that we are looking to the past of the event horizon at which the area has stabilized to some value. And of course, this assumes the null energy condition. We assumed the null energy condition to derive the Raychaudhuri equation. So this is the Raychaudhuri equation. And essentially, in applications to the quantum extremal surface, we apply this inequality in the reverse direction. So usually, we have a QES somewhere at which the derivative of Sgen is negative. Sorry, not negative. What am I saying? It's 0 because we have found a stationary point. And as we move this point to the future, d plus of Sgen can only become negative, right? Because its derivative is negative. So if it starts at 0, it can only become negative. It also means that if Sgen here is something finite, and everywhere its derivative is negative, even here, the Sgen should be smaller than before. Than at QES, right? So, but you see, Sgen has a piece which is the area. And as we approach the boundary of ADS, the area is increasing, right? So this usually means that the QES cannot be in front of the horizon, because if it was, then if this light ray reached the boundary of ADS, we would have Sgen being very large here, just because the area at that point is very large. So that's the reason why QESs usually lie behind the horizon. Is that argument clear?
Yeah.
By the way, Jung, should I ask, I can also move to a different place. Is there too much background noise, or is it fine?
Up to me, it's okay, but it's up to you. I mean, so far, I think it's
fine.
okay, but
Okay.
yeah.
All right.
If you are comfortable, you can, I mean, keep going. But if you are not like comfortable, also
No,
it's
no, it's
okay.
fine. It's fine. If it's okay with you guys, then I'll just keep going here. So that's why the QESs generally lie behind the horizon. So let me draw another thing here. So we have, let's say, the horizon. So we have some singularity. We have some, let's say, ADS future. So we have the horizon here, right? Here, Sgen prime is 0. So we expect that in the past, Sgen prime is positive. This is what we have seen. And essentially, when we move downwards in this direction, we expect the generalized entropy derivatives to be positive still, right? Because of this area term is big, it's increasing. So we generally expect that as we go to the right of the horizon, Sgen prime sort of stays positive. So if the derivative this way, is positive, then it means that the QES where Sgen prime is 0 generally lies to the left of the horizon. But notice that here we use the fact that the black hole is not coupled to anything else. Like it's not like the boundary is interacting with some other system in the presence of a heat bath or something like that. So this is why when we have a heat bath, the black hole, the quantum extremal surface can actually lie in front of the horizon. Let me explain that in our example. So the examples that we have been doing. So the extremization condition was at finite temperature phi r 2 pi over beta 1 over sinh 2 pi a over beta equals c over 6 sinh of pi over beta a minus b divided by sinh of pi over beta a plus b. Okay, and just to make life simple, I will just look at the 0 temperature limit of this equation as beta goes to infinity. Phi r 1 over a equals c over 6, a minus b over a plus b. And this implies, as I mentioned last time, the left-hand side is positive, so the right-hand side also has to be positive. This implies that a is bigger than b. Okay, so let's see how we could have concluded a greater than b without knowing the extremization condition. So we will show that actually QFC implies a greater than b. Okay, so let's see how that works. So we have here, by now familiar ADS, we have the Poincare patch at 0 temperature. We have this thing here. We have here the point B, right? Let me draw this a bit further out. Let me draw the point B here. If A was less than B, let's assume for the sake of contradiction that A is less than B, then this means that the point A is here. So the QES is here, the point Q, which is closer to the boundary than this. So this is the interval that we are considering. And it means that when we shoot a light ray here, it hits the boundary first before meeting the light ray from B, right? This is crucial. If A was bigger than B, on the other hand, if like A was over here, then the light ray before going all the way to the boundary would intersect B if A was much bigger than B, right? So the point is we want this kind of a situation, not the other kind of a situation. And again, the argument is similar. If it had been the case that we have little a, for example, lying here, let's say the light ray hits the boundary here, right? We can run the same argument. The SGen prime equals 0 at the point negative a. So at the point capital B, it must be negative by QNEC, by QFC. But that's a contradiction because a point B is at the boundary. Okay, so this situation cannot happen. A less than B cannot happen because of the quantum focusing conjecture. If at the QES, the derivative of SGen is 0, in the future, the derivative of SGen has to be negative. And that's not true in this situation. So what actually happens is that—
Could you say why is it not true? I think I missed the important point here.
Because SGen double prime is negative, right? This is the quantum focusing conjecture.
Yes.
SGen prime at the QES is 0. Right, so let's say the QES is here, and you shoot this all the way to the boundary, to the point B. So this means that SGen prime at the point B has to be negative, right?
Right.
Because second derivative is negative, so the first derivative must decrease.
Mm-hmm.
But the point B, you're getting very close to the boundary where the dilaton is blowing up. Right, so this is what I was saying before, that SGen has a term which is phi plus some S
increase.
matter.
Yeah.
Yeah. So phi is huge and it's increasing towards the boundary, right? That's like sort of where the anchor is at infinity, and we don't change that. So this is a contradiction.
Okay.
So just to drive home the point, if it was the opposite, if A was greater than B, then we have this point deeper in the bulk, and we shoot this light ray, and we have this light ray coming in. The point is, the interval whose entropy enters the generalized entropy is this interval. So the QFC can only be applied up to this point, up to the light cone, in the causal diamond of the interval that you're considering. The QFC is not true beyond that, because if you want to go beyond this thick point intersection I, then you have to include the matter degrees of freedom to the right of B, but we are not doing that. So So that's why A greater than B is okay. So it's fine. Sgen prime is 0 here, and it can decrease up to the point I. And that's no problem because I is not at the boundary. Okay, so what's the time? Let's see. Okay, so in the interest of time, let me stop here with the applications of the quantum focusing conjecture. Maybe the takeaway message from all of this should be like this picture here, or these two pictures here. In the classical application of the focusing conjecture, we work in this picture over here, where the area derivative has gone to 0 in the future. We have some stationary black hole. And then the second derivative being negative tells us that the derivative of the area must have been positive in the past. And this was Hawking. In the quantum extremal surface applications, we have the opposite. We know that somewhere the derivative is 0. So in the future, the derivative must be negative. And this underlies all applications of the Raychaudhuri equation to entropic problems. Okay, are there any questions about this? Okay. All right, so with this, maybe let's take a 2-minute break, and you can maybe, if you have some more questions about islands or quantum extremal surfaces or page curve, I'll be here. But after the break, we will go into like the replica trick and replica wormholes, like a brief introduction to that. Okay, so I'll just take a couple minutes break here. There's a question in the chat. Yeah, those lectures will be available on YouTube, I believe, after some editing. Okay, so if there are no questions, let me go to the replica calculation, the replica trick. So the replica trick is based on the simple observation that the von Neumann entropies trace rho log rho with a minus sign. This log is a funny function. It's not really nice or analytic, so we don't want to deal with logs. We instead want to think of log rho as rho to the epsilon when epsilon goes to 0. Right? Roughly speaking, rho to the epsilon when epsilon is small is 1 plus epsilon log rho. So this is like rho to the 1 plus epsilon. Oh, did I lose my internet? I should be fine.
No,
Okay.
it's okay.
It's fine. Okay. So it's rho to the 1 plus epsilon, but even fractional powers are kind of weird. So we just want to consider integer powers of rho and look near n equals n goes to 1. So this is the quantity that people study. Instead of studying trace rho log rho, we study trace rho to the n or integer n. And if the gods are kind, this function is analytic in n, and we can just go look near n equals 1 and find the entropy. Okay, so this is called the Renyi entropy. Okay, the Renyi entropy has some logs and stuff like that. It doesn't really matter, but the point is we're computing trace rho to the n. Okay, so also nice is that this quantity has a simple path integral representation. So let's see what's rho and how we can compute it. So let's say we are in the ground state of some system, ground state of some QFT. Let's say just on R1. Okay, so it's a 2D QFT, spatial manifold R1, and we're looking at the ground state. We ask for S, we want to study, not S, let's say rho of some interval AB. So we have here the line, we have here A, we have here B, and we want to study rho AB and traces of rho AB to the n. Okay, so how do we first, let's prepare the global ground state. So the ground state. The ground state is prepared by doing Euclidean time evolution over the past infinite line. So if we do a path integral over R1 times R negative, we prepare the ground state. So if we do the path integral over this geometry, we prepare the ground state. And we have psi, as a functional of phi of x, where x is the coordinate along here. Phi of x is the sort of a field configuration, and the output of the wave function is some complex number. So this is some complex number. Okay, so this is the computation we do. But what's rho is like we have to take the bra and the ket and trace out things outside of the interval AB. So what that means is we bring in, so now this is the bra side, this is the ket side, and tracing, so there is A, there is B, so this is our interval, AB, right? We don't want to trace over AB, but we do want to trace over this region. So we glue these together. So these get glued, but here we don't put anything. So, rho is a matrix. It has two arguments. So we have phi 1 of x, phi 2 of x. Again, this is some function, right? Phi 1 is this boundary condition here is phi 1. Here it's phi 2. And that's it. So if we do the path integral with these boundary conditions, now it's over a plane, but with a boundary condition specified just below the interval AB and just above the interval AB. So that's like rho AB with two arguments. If we want to now just compute trace of rho AB to the n, we just need to take n of these, right? And contract the column index of the first row to the row index of the next row, column index of the second row to the row index of the third one, and then back. So what that does is makes like n copies of these systems and glued in a particular way. So that's called the replica manifold, usually denoted Mn. And the QFT partition function on Mn equals trace rho to the n. But the rho defined this way may not be normalized. So if we denote this QFT partition function on Mn by Zn, trace rho to the n is Zn over Z1 raised to the n. So this is like trace rho whole to the n. Usually trace rho is normalized to 1, but if it's not, then this is how we should compute it. Okay. So fine. So we just need to compute the partition function of a complicated QFT. There's a question. No, so there is only one way to glue because, for example, trace of rho square is like let's say rho cube is row AB, not AB, AB was it IJ, row JK, row KI, right? So this slot here has to get glued to this slot here. And this slot here has to get glued to this slot here. And then this has to get glued back to here. So there is sort of a cyclic way of gluing it. And that's the only way. Okay, so we have to compute this object. Okay, again, this is hard to compute. We don't know in field theory how to compute it. But if the field theory was holographic, then Zn has a ADS realization. Zn can be computed using gravity. If QFT is holographic. Okay, and that's what we will do. So this is following the footsteps of Lewkowitz and Malacena. The thing that has to be emphasized is that this replica trick is done on the boundary, right? Entropies are defined usually in non-gravitational theories, and they live on the boundary. So essentially, we set up some boundary conditions at infinity. So the way it's usually drawn is that here I'm drawing, one copy of the boundary, and then here is sort of a second copy, right? And then maybe there's a third copy. So this is like computing trace rho cubed, where these sort of kinks represent the fact that the boundary conditions may not be, constant. There may be some non-translation independent boundary conditions depending on what exact state you're considering. Okay, the point is there's a Zn symmetry here on the boundary, right? There's just the symmetry that exchanges this row with this row, this row with this row, and then back. So cyclic permutations are a symmetry. And what we assume is that in ADS, we are supposed to take these boundary conditions and fill in the bulk and find the saddle points of the bulk Einstein equations. And we do that, and we assume that the bulk saddle has also the Zn symmetry, has also this Zn symmetry. Okay, so usually what will happen is there will be a fixed point of this Zn symmetry, and the bulk will look like three identical things sort of glued together. I have done a very bad job of drawing this, but essentially there would be some geometry, which is just sort of cyclically glued together 3 times. And this geometry is completely smooth, and it's just some solution to the ADS equations with specified boundary conditions. And all we are supposed to do is that Zn is supposed to be exponential of minus the on-shell action, right, of this saddle. Where the end dependence comes in is in the boundary conditions. The saddle depends on the boundary conditions we put in. On-shell gravity action. Okay, so that's what we have to compute. Basically that's it. And you can show then following some steps for which if we have time, maybe we will go through them. But if not, I will recommend some other lecture that was given in August in ICTP in Trieste. But this is morally how you set up the problem. So you have some partition function on some replica manifold. You're supposed to compute it and take the n goes to 1 limit. And I have drawn here particular examples of trace rho cubed and so on. The point is that these page curves are also present in trace rho squared, like we discussed last time. So in order to see this dominance of saddles, it's not, we can take the limit n goes to 1, but it's already good enough just to work with n equals 2, the 2 replica object to see how these replica wormholes kind of arise. Okay, are there any questions about this?
Is this obvious that there has to be a fixed point in the bulk for the Zn?
Yeah, no, in all of these, I think rigorous results are just absent. And what you should think of this derivation as capturing is it captures a large class of interesting examples that most likely you will encounter something that falls in this class.
Okay.
And yeah, if you have some more complicated setup, then you basically have to follow these steps and make sure you're not making a mistake. It could happen that why does the bulk have to have the Zn symmetry? That's not also obvious. But this is sort of the vanilla situation. Like if you have these bunch of simplifying features, if the setup of your problem has those features, then you can proceed on this logic.
Okay.
I think Jeff Pennington and Chris Akers have discussed some situations where there is some interesting analytic structure in N, and involves even in this paper by the Stanford group from last November had such examples. So one has to be careful, but this is sort of the basic Faulkner, it's not Faulkner, Liukowitz-Maldacena logic.
So in the bulk, is it also smooth at the? Is there any like conical singularity?
Yeah, no, there is no conical singularities because we're finding an honest solution to the bulk equations of motion.
Mm-hmm.
And here it looks like this angle is 120 degrees, but that's just me dividing up the geometry into 3 pieces. Really, you have maybe no right to look at these lines, and then it's just a completely smooth thing, right? You go in, it's smooth, everything is smooth. There's no funny conical angles or anything.
But
I
there
think we
could
will
be
have,
some many,
yes.
like I said, yeah, there could be some many things. I mean, it's gravity,
Yeah.
so you can also consider some conical singularity geometry, but it's not allowed in this calculation.
The thing with the conical singularity is that it doesn't solve the equation of motion at that point where the conical singularity is.
I see. Okay.
Right. So because the curvature is infinite there, so it's not an honest saddle.
I see. Okay.
The conical singularity does come in, but it comes in a subtle way, which I think maybe we will have time and then I can describe. The conical singularity is basically a trick in order to take the n goes to 1 limit in the Liukowitz-Maldacena setup. But strictly speaking, and the conceptual breakthrough of Liukowitz and Maldacena was to realize that there is no conical singularity in the bulk. Okay, all right. If not, then let's just discuss really quick what happened. But Jungi, what you said is true that in the bulk, there could be multiple saddles, that dominate this computation. And that's basically when you have 2 possible Ryuta-Kiyanagi surfaces, and they can compete and they can exchange dominance. So one can indeed have multiple saddles, and then depending on which saddle has lesser area or lesser action, that one wins. The saddle with the minimum action wins. And dialing some parameter, you can have some phase transition in which saddle is the dominant saddle. And this is indeed what happens between this phase 1 and phase 2 of the page curve. Okay, so let me describe that now in a very simple model discussed by PSSY. So what is this model? Okay, this model even simplifies. It's simpler. One of the model is simpler than even JT gravity. What you do is simply keep in the Euclidean action the topological term, the phi naught term. So the dilaton is gone, like there is no fluctuating dilaton. Like we just look at this, and this is equal to negative phi naught times the Euler character. So the weighting is e to the minus I, which is e to the phi naught times the Euler character of the surface. So if you have a disk, which is what we typically have, then the disk has chi equals 1, and we have a weighting e to the phi naught. Just to conform to convention, I will just rename this phi naught to be S naught. So we have a gravitational action in which the disk geometry comes weighted with an e to the S naught. Okay, but what's their model of the internal modes and the Hawking radiation? We have to set something up. So what they assume is inspired by this paper of Korkulu and Maldacena. You model the internal states of a black hole by some end of the world brane. So what is an end of the world brane? It's very simple. Usually, we would have some black hole here, and we would have a horizon, right? We can have even this horizon. And usually on the other side, the space-time would go on to some other asymptotic boundary. But there are some geometries in which the space-time just ends. And okay, you have to satisfy some junction condition, etc., at this boundary. But essentially, you can write down equations of motion and write down solutions where the action looks like the above action, I gravity, plus some mass times the proper length of this trajectory that on which the particle lies. So if the particle follows some geodesic, and the presence of this mu sort of distorts the geometry a little bit near its location. So these are the models. And so we assume that this particle inside has k possible states. Okay, it could be like a spin 1,000 particles. So if it has a spin 1,000, it has m quantum number, which can take 2001 values. So that's the parameter k, and we have a parameter e to the S naught. And the competition will be, as you can now see, between k and e to the S naught. Which one is larger, which one is smaller? It's like the m and the n we had in the Gaussian example from yesterday. You had two systems, one with Hilbert space dimension m, the other with Hilbert space dimension n. Okay, but so what we do is we try to entangle this end of the world brane particle with some heat path. So here is some heat path. Or not just entangle this particle, but entangle the gravitational system with its k internal states to this heat path. So our state that we consider is 1 over square root of k, sum over I from 1 to k, psi I of the gravity. Gravity means the JT plus, or not the JT, this topological thing plus the particle times some state in this heat path or the radiation. Okay, so that's our global state. It's exactly like what we had before, like yesterday. Maximally entangled state, Cij, Ij with some Gaussian weight. Here there is no Gaussian, we just take it to be maximally entangled like this. Okay, the important thing is that these are orthogonal because it's just some quantum system, we can pick them to be orthogonal states, but we make no statement about the inner product of psi I with psi j. So we don't commit ourselves to picking orthogonal states. These could be non-orthogonal. Because the definition of these states is from a gravitational path integral, and we don't want to make statements about if we prepare a state using a gravitational path integral, is it orthogonal, is it not orthogonal? So we want to keep that general. And then the idea again is to derive the page curve is we want to compute the entropies of the radiation region. But we won't, again, compute the entropy here. We will just compute the purity. So we just want to compute trace of rho radiation square. Okay, so first we can compute rho radiation. So for that, we need to take 2 copies of the state psi, a bra and a ket, not 2 copies, I just mean the bra and the ket, and do the partial trace over the gravitational system. So what that gives us is 1 over k inner product psi j, psi I, right? I, j. Sum over I and j. I'm going to omit the sum. So this is the density matrix of the radiation, whose ijth element is given by the inner product of these states, psi I and psi j, in the gravitational sector. Okay, so what's the trace of rho radiation square? We now take 2 copies of this and take the trace, right? So that's psi j, psi I, and in the other term, right, psi I, psi j. So it's absolute value square, and sum over ij with some normalization factor, 1 over k square, sum I and j. So this is the object we want to compute. Inner product psi I, psi j squared. Okay, and we want to compute it using gravity. So like any computation, so notice that now the radiation system is gone, right? These were gravitationally defined states. So its inner product has a gravitational definition. And as like in any quantity in gravity, these are computed by specifying some boundary conditions. And we specify the boundary conditions and let the geometry do its job, fill it in whichever way it wants to. Okay, so we have this inner product psi I, psi j. So now I have to explain to you a little bit how these psi I states, these Korkulu-Maldacena states are defined. So what is the state psi I? Okay, it's a pure state, but so let's do it in steps. One thing we do is on the boundary, right? We can do a path integral on a circle. It's a 2D gravity, so its boundary is 1-dimensional. We can have an S1 boundary. If we have an S1 boundary and we fill it in, we compute things that are like, Z or entropy of a black hole and stuff like that. But let's imagine cutting this. If we cut this and only do a path integral over a semicircle, so let's say this has length beta, this has length beta over 2. What this creates is a thermophile double state. So, along this line, there is usually a horizon here. And if we prepare the state and let it time evolve, in the Lorentzian section, it gives us this kind of a geometry. So this is the usual. If we just look at one side, we get a thermal density matrix. The global state is some thermophile double state of the left and the right system together, and we have some horizon. The Korkulu-Maldacena state is you chop the semicircle into another half. So you cut it out. So you only have a quarter of a circle. Okay. So here is the asymptotic boundary. This is the thing that will become the ADS boundary if we evolve in Lorentzian signature. Here, you have to end it, but you have to specify some boundary condition. And this is where the index I lives at this point. And what this does in the evolution is in the Euclidean section, it follows some Euclidean geodesic. And then when you become Lorentzian, it follows some Lorentzian geodesic. So this is like a boundary of space. So this is the ADS boundary. You start going in, and the space just ends at this particle labeled by I. And you can have various different boundary conditions here. And in Korkulu-Maldacena, these I's corresponded to various Fock space states of the SYK model. The SYK is a bunch of fermions. There's some Fock space. And you can just say, I want to study a particular pure state in that fermionic Fock space. And that's what this index I sort of corresponded to. Okay, so these are the states, right? So the takeaway message from this discussion is that the state psi I is defined by a path integral, a gravitational path integral, whose boundary is sort of looks like this. with some index I here, the free index I. This is the state psi I. Okay, so what will be the boundary conditions for psi j, psi I to compute this kind of an inner product? The answer is obvious. We will have some kind of a semicircle with the index I here, the index j here. And we can fill in the state however we want. So this is the boundary condition. We can fill in the bulk however we want. Okay. So let's fill it in. There is only one obvious way to fill in this. Ij is to just make it into a disk, right? We make it into a disk.
Can I ask? So
yeah,
what is the length now of this? Is still it's beta by 4 now?
it's beta over 2 because there's beta over 4 and beta over 2. But we will work in this topological theory, so the lengths actually don't matter. But yeah, if you were doing it an honest computation in an actual theory, this would be a total length beta over 2.
Okay.
Yeah. Right. So, but we can write down now just the weight of this. So we filled it in using a disk. So this is a disk geometry. So we have e to the s naught times delta ij, right? That's the inner product. I and j have to match because a brane of type 1 stays a brane of type 1 as it moves through the bulk. So this is what we get. So we roughly get that psi I, psi j is like e to the s naught times delta ij. Okay, but now let's also try to compute directly psi I, psi j, psi j, psi I, right? This was equal to trace rho square from our previous sum over I and j from the previous formula. Now the boundary conditions are two of these. So we have I, j, right? And on the other side, we have I, j. So these are the boundary conditions. So this is like setting up the Liukowitz-Maldacena problem as boundary conditions. This is a toy model. It doesn't look like it, but it's the moral analog of that step where we set up the boundary conditions corresponding to computing some quantity. Okay, so there are two ways to filling it in. So the filling number one is we just make two disks, ij, ij, and we close this up. So there are two disks. We have e to the 2s naught, and we have delta ij, right? Delta ij squared is just delta ij, but then there's a sum over I and j. So delta ij just leaves one sum, so we get e to the 2s naught times k. And this should remind you of a term from last time, like m squared times n. That's that term. Okay, but there's a second filling because in gravity, we only specify the boundary conditions. We don't control what the bulk does. In that, we have these two. This guy can join up here, and this guy can join up here. Now the geometry is just one disk. So we have e to the s naught. We have e to the s naught, right? But there's no delta functions in I and j. So there's sum over I and j. So notice that e to the s naught is smaller than e to the 2s naught because we imagine s naught to be huge. So we are small compared from s naught, but we are large in k. We have k squared because the sum over I and j is unrestricted. So this is like the term m times n squared from last time. So the total trace rho square is like m squared n plus mn squared. And okay, there is some normalization factor. Like there is a 1 over k square just sitting here. And there would be a e to the 2s naught from normalizing the psi i's properly. Like their normalization has an e to the s naught. So essentially you get mn to the -2 again, which was the same as before. m-1 plus n-1 we found last time. In this case, it is e to the minus s naught plus k inverse. So case 1, k is much, much less than s naught, right? This is like when there is not too many internal states. This is like the early part of the Hawking radiation, when the black hole is big and the radiation and the internal particles are not that highly entangled. The number of internal states is small. And then trace rho square is just k inverse. It's like the Hawking result, right? K was the dimension of the radiation system. Case 2 is k much, much bigger than s naught. Trace rho square is e to the minus s naught. This is like the flat part of the curve where you don't, you just stop growing. Even though k was increasing, you're trying to, as soon as k becomes larger than s naught, it's impossible to fill the black hole with more than s naught states. Okay, so just to draw what the island looks like. So in case 1, we have this end of the world brane, and the entanglement wedge of the black hole is the whole thing. So this is the entanglement wedge of the black hole. There's a horizon here, but everything inside the horizon, outside the horizon belongs to the black hole. And this is case 1. Case 2 is the internal region. Now there's a lot of entanglement, k is very large. So the internal region should belong to the radiation. And indeed, you get an quantum extremal surface here, and the black hole is responsible for only this part of the spacetime. So now this is the entanglement wedge of the black hole. Okay, with that, we finish the, so you see, so what is the replica wormhole? This geometry right here is a replica wormhole. What are the replicas? The replicas are these 2 boundary conditions that we set up. This is replica number 1. This is replica number 1. This is replica number 2. And there's a wormhole because we connect the replica number 1 to the replica number 2. Here it's disconnected. This is disconnected. This is the usual vanilla geometry. And in this simple model, you can actually do more. You can compute trace rho cubed, trace rho to the 4th, trace rho to the 5th as functions of e to the s naught and k. So it's possible if you take e to the s naught large and k large with ratio fixed, you can compute trace rho to the n for each n, and then take the limit n goes to 1 and so on and so forth, and get the entanglement entropy. And because you're doing a precise computation and not just some saddle point in this limit, you get a continuous curve. You don't get a sharp transition. You get a crossover from a linear behavior to this. So this is k, and this is s. And here the transition is when k equals e to the s naught. And you can find out what the form of this curve is in this model. It's smooth. Okay, are there questions about this?
So this argument is just specialized in the 2D JT gravity, or is it some general for any?
No, it's more general. So what you can show, for example, there was this other paper by Almeri, Hartman, Shagulian, Maldacena, and Tadjini, which did it for the kind of setups we discussed in the bulk of these lectures. like the eternal coupled ADS black hole to flat space. So you can write similar diagrams and similar equations, and you get similar results. The point again is the competition between, cost in area, which is, penalizing you. So if you include the island, you go from e to the 2s naught weighting to e to the s naught weighting, but you save in entropy, save in s matter, is because, you go from k to k square. And at some point it becomes beneficial to switch to the k square if k is too large. So this competition is a feature. Whenever you have this, you will have the replica wormhole coming into the picture. Yeah, those computations in this paper by are more complicated, so I couldn't go into them here. They involve knowing a bit more about the boundary particle in JT gravity and solving something called the conformal welding problem.
Can I ask a question?
Yes, please.
So your assignment of this psi I with quarter of beta, can you explain again? I mean, why you have quarter of beta there?
The quarter of beta was not super important to this argument, as I answered in response to Arif. Is just that in the Korkolu-Maldacena paper, they decided to do it this way. So, but the basic point is you're doing a path integral over a line segment of some length, L. We can just call this length L. And this psi I, the wave function, is a function of the boundary condition on the other side. Here is X. So we interpret I as labeling the state and the boundary condition on the other end as going into the argument of the wave function. And in the setup, the L, the length of this interval along which we are doing the path integral, gets related to the average energy of the state by sort of tracing the steps backwards, like going like this and going like this. So what this L sets, it sets the energy of the state, basically. If you want, we can set L to 0. That would be like taking a very, very high energy state. It would be like if we take L to 0, let me say here. So, the SYK spectrum, we have energy here, and the spectrum looks something like this, right? These are some pure states. So what that L is setting is which pure state we pick. Do we go here? Do we go here? Or do we go right in the middle of the spectrum? Right? And those states are basically like up, 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 down, 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 states like this in the fermion-Fock basis. So we start with such a state, which is a very, very high energy. It's in the middle of the spectrum. And then we apply a tempering to it. We temper it, we lower its energy by applying something like e to the minus beta over 4 times h. So that is why I was writing beta over 4. But in general, you could just write here some e to the minus LH. And its purpose is to take this Fock space state, which lives sort of in the middle of the SYK spectrum, and make it slightly less energy, slightly less energetic.
I see. So beta over 4, so in that sense, beta over 4 is a kind of convenient choice.
Yes, exactly. Yeah.
Okay.
Yeah. If you take L to be beta over 4, it tells you that the energy of the state is like the thermal state at temperature beta. the typical energy of the state would be like that. The average, the expectation value of the energy. Yeah.
Could you please comment on how, maybe you're planning to do this later or not, but how this ties into the, the idea that what one really is talking about is the ensemble of theories.
Yeah, okay, good. So, okay, I derived here two things. So there is this equation here we derived. We said psi I, psi j, right? We concluded it is e to the s naught times delta ij. But then I also computed for you psi I, psi j, psi I, using this kind of boundary condition, ij, right? And here we found e to the 2s naught delta ij plus e to the s naught with nothing, right? These equations are inconsistent with each other.
Right.
Right? If I square the first equation, I don't get the second equation. So the way to interpret this is that there is actually some secret expectation value sign in these equations. And this expectation value sign is sort of, think of it as the averaging over the ensemble of the SYK theories. Because now they are consistent. If I put expectation value there, now it's consistent. These equations are consistent. So what it means is that if you compute in a theory of gravity, like these path integrals, they are inconsistent with a single underlying theory of gravity, a single underlying boundary theory. But they are consistent with some ensemble averaged duo. That makes sense?
Yes, although I don't see how putting this E makes the second equation consistent with the first, but
It's just that the it's not well, it's not. There is no obvious contradiction now, right? Because
right. Yeah, right.
Because the expectation value of a random variable is not necessarily the expectation value of a random variable squared.
Right.
So there's a question in the chat. Yeah, okay. It's just this, right? So without the expectation.
So you have some variance now.
Yeah, you have some variance, and the variance is set by the second term, right? So if I literally interpret this as a real number, then if I square the first equation, it's not equal to the second one. But if I think of this as some kind of a random variable over having some probability distribution, then this is like the mean of that, right? And then this is the expectation value of the square of that random variable. And yeah, so this is not equal. So that's why it's consistent. So, or yeah, there's no obvious contradiction. I hope that answers the question in the chat as well. Yeah, exactly. So they're not inconsistent after you put expectation value signs. Okay, any more questions? Okay, so in the last 10 minutes, maybe I can go back to this Liukowitz-Maldacena argument because I think it's interesting and just see where the conical deficit sort of comes in. Okay, so we have to do the following. So we have to take trace rho to the n. We have to take a log and we have to take a 1 over n minus 1. And in the limit n goes to 1, this is precisely negative trace rho log rho. Okay, so this is the quantity that we consider. So this is equal to minus 1 raised to n minus 1 log of zn over z1 raised to n, right? Where z's are these partition functions with the correct boundary conditions. That's equal to 1 over n minus 1 log of zn minus n times log of z1, right? And because there is a zn symmetry, the first term is also n times something, right? So I'm just going to write this as log of zn divided by n minus log of z1. And this object, we had, I'm just going to draw it like 4 ways now. So, sorry, this is really bad. Let me just draw it as a circle. And we have these 4 and with 2 pi. So this is supposed to be the n equals 1 geometry. This is supposed to be the n equals 4 geometry. And they look the same, but they're different. So, maybe there is some stuff. Okay, this object here is the action of one of these pi wedges, right? So this wedge, a contribution of this wedge, the action is just 1/4 of the total action. Log of Zn is the on-shell action. And 1/n of that is just the action from this pi. Pi, I meant PIE, like this little section of the pi. Okay, but now we have to add and subtract something. There is no conical singularity here, right? The angle is 2 pi. So if you naively think of, this contribution, one should really excise a little piece close to it. And this is the thing, right? So this contribution is equal to log of Zn over n, because a little disk doesn't contribute anything. So it doesn't take us anything to take it out. But, in order to compare it to the disk, it helps to put in the conical deficit and subtract it. So we add this little piece and subtract the conical deficit, just sort of near the horizon. So this is the horizon, we subtract this. So this is the log Zn over n is equal to the term A minus the term B. Okay, but we also have negative log of Z1. And the angle here is 2 pi over n, right? It's 2 pi over n, this angle. We've added and subtracted a conical deficit. Okay, but what's Z1? Z1 is just the geometry with angle 2 pi, right? Angle 2 pi. And there is an overall, this thing multiplied by n over n minus 1. There was this n over n minus 1 here. Okay, but notice that A minus C is of order n minus 1 squared. Why? Because C is the saddle point. It's the correct saddle point when the angle is 2 pi, right? And so when n is close to 1, the geometry A is just a variation, is a first order variation away from a saddle point. So, any configuration minus the saddle is at least quadratic in the deformation parameter. That's what it means to be a saddle. So it's equal to n minus 1 whole squared times something at least. And in the denominator here, we only have n minus 1. So that term is going to go away. So A minus C sort of cancels. And the only term that contributes in the n goes to 1 limit is this little conical deficit piece here. And its action is linear in n minus 1. So it's a simple exercise to compute. You have a little cone times the transverse space. What's the action of this cone? You have to use the Gauss-Bonnet theorem and plug it into root GR. and it's linear in n-1. It's linear in n-1. So that cancels the n-1 in the denominator, and you get a finite answer for the von Neumann entropy. So it's a bit subtle, like this Liukowitz-Maldacena argument. Let me recap it. So we start with Z, this entropy, the Renyi entropy here, trace rho to the n. It's equal to Zn over Z1 to the n and a log. We write it like this. We take out an n. So this log Zn over n. And we had assumed that the bulk has a Zn symmetry. So we just look at 1/n of the geometry. And 1/n of the geometry, it looks like it has a conical deficit, but it's not really there because the total angle was 2 pi. But it's helpful to put in the conical deficit and subtract it. Why? Because then we can take the geometry with the conical singularity, this A geometry, and compare it to the actual on-shell geometry at n equals 1. And in the n goes to 1 limit, the difference in action being quadratic makes it go away. So A minus C vanishes in the n goes to 1 limit. And that's why we are left with a contribution from the term B. And it's the reason why entropies are localized at the horizon. It's why entropy is proportional to the area of the horizon. Essentially, this two-dimensional space, the time and r, gives n-1, which cancels the n-1 in the denominator here. And the rest, the transverse space area, just comes for the ride. So this is also like a nice way to see why the entropies are proportional to areas of the horizon. Okay, I'll end there and take any final questions. Thank you.
Thank you very much for the great, clear talk. And yeah, please ask a question first. Yeah. Actually, I have a question.
Yeah.
So here yeah, it's very nice to understand this Maldacena argument, but I don't see how this saddle is changed, or I mean, here I can see that some horizon or give a contribution, but like some other saddle, like how can we explain this page curve in this like replica?
Right.
Case?
So right. So the page curve.
Yeah,
so there
from
are
the Maldacena
so
argument.
Yeah, this is just one saddle, but we could also have multiple saddles with Zn symmetry, right? So what happens in the page curve arguments is we have two different saddles. Both of them have Zn symmetry.
Yes.
And on each of them, we can apply this argument.
So B is changed in the new saddle also. This
Yeah,
A
B
minus
will
A.
change. Yeah, exactly. The B will change in the two geometries. Because so it doesn't come out in these things, but you know, the geometry here is really not just 4 times this geometry. It's something else.
Yes.
It's a different boundary condition, different geometry. So
here, in this setup, maybe you can also put this bath, but in this slide, you don't consider like a bath. Or
a bath, yeah. I did not, but it's the same. Like you can do the derivation with the bath. It doesn't change very much. The basic ideas are still the same.
I see. So without the bath, you can also still, there could be also new saddle.
Yeah. Even without the bath, for example, if you set up in ADS3, you know, the problem of computing the entanglement entropy of two intervals like this. So if our region A is like this, you know, union this, then depending on the cross ratio of these 4 points, you know, the root Hakenagi surface either looks like this or looks like this.
Yes.
So this is the simplest example of when you have two competing saddles. and one wins over the other. Here, the controlling parameter is not some time or anything. It's just a cross ratio of these 4 points. So
Yeah,
this
in
would be
this
similar.
case,
So if you run the Leukowitz-Maldacena argument on this, you would also have two saddles, both of which are Z-n symmetric, but their values of the B term will be different.
yes, so this entanglement argument is very intuitive because I can see this Replica surface and definitely they are two different Replica surface.
Yeah.
But
Even
Replica
here,
case,
yeah,
Replica case,
case,
to me,
yeah,
it's
yeah.
still I can accept that there could be some use set, but it's hard to see, but intuitively. But okay, maybe.
Well, it's, for example, in this example, right? In this simple example where the
This is
geometry.
also, yeah. In this example, yeah, it's also clear, but the usual, yes. This example is clear, but like a usual some 2D CFT, some holographic CFT, and you just replicate it.
Yeah, yeah. I can maybe say some words. So in this AHMST paper, what happens is you're trying to compute the entropy of some bath region. So you have these twist operators inserted at the endpoints of the bath, right? Like the interval whose entropy, like this B to infinity region. So you have a twist operator at B, and you have a twist operator on the other side, right? In principle, you might think those are the only two twist operators, and you compute with that. But what can happen at late times is that it becomes beneficial to nucleate two twist operators in the gravity region. So because gravity is fluctuating, it becomes dynamically favorable to put extra twist operators. So the twist operator putting it costs you, again, some area term, like some 1/g cost. But then the correlation function of 4 operators might be smaller, right? Because the correlation function of 2 operators, if they're very far, is like the length of some geodesic between them. But if you nucleate 2 more, then you might just have 2 short geodesics close by. So again, it's a competition between the 1/g term and the matter entropy. But you do need to set up a situation where the matter entropy term is important. Otherwise, you will not. Otherwise, the one with the island will never dominate.
Okay, thank you. Yeah, please ask any questions.
I got a question.
Please. Yeah.
It's not a question. Asking about your opinion about future problem, unsolved problem, and the main issue left to be understood.
So, yeah, I think there are some interesting future directions, but they all seem a little bit unclear how to make progress. Sorry.
Yeah, also there are many students, so please, I mean, so it would be very helpful to students to study in future. So please ask.
Yeah, let me just list something. So as I said, we don't have a way to compute rho ij itself of the final state of the Hawking radiation. We can compute some special quantities like trace rho log rho, or some average values of some observables, but we don't know this. And it seems this question seems just out of the present day technology of what we know about gravity and so on. So what is the description? What is the in the CFT of physics seen by infalling observers? So here, you see, again, I want to emphasize that the page curve and this quantum extremal surface has solved one very specific problem, which is the entropy question. We don't know, like, if an observer goes behind the horizon, how does he describe the physics? And then naturally the question is, what happens to the singularity? Okay, some might have hoped that this page curve mismatch between Hawking's answer and Page's answer would be a window of opportunity for quantum gravity to come in and resolve the singularity and tell us how this curve is supposed to come down. But the quantum extremal surface allowed us to cheat. It had to know nothing about the singularity, and just putting some of these saddles gives us the correct answer. So we still have no idea how the space-like singularities inside black hole horizons get resolved, or what their endpoint is, what their fate is. And I believe that 1 and 3 are kind of connected. Like, to answer 1, you kind of have to know 3 and so on and so forth, because the singularity disappears, creates a pure state on the outside. On number 2, there was a very interesting recent paper by Jaffris and Lamprou, which I encourage you to look at. And these people have also given talks. Yeah, and for this, some more progress was made by Douglas Stanford in his most recent single author paper. It was called More Quantum Noise from Wormholes. So he still found required some disorder averaging, but he's sort of trying to compute more properties of the state, like some correlation function in this state. But it still requires some disorder averaging. Yeah, I think these are sort of the big open questions. And of course, there is some questions about how do these islands or quantum extremal surfaces imply for cosmology. And now we know that black hole entropy sort of really is some microscopic counting of some states. And this quantum extremal surface formula really enforces the purity of states, the fact that the entropy of a system is equal to its complement and so on. Does the de Sitter entropy have similar meaning? And so far, people have written papers about islands in cosmology and so on, but I don't think any of those papers has gotten close to this question. Like, it always ends up being some kind of Schwarzschild black hole in de Sitter space, and you end up probing the black holeness of the black hole horizon rather than the cosmic nature of the cosmic horizon. And here there was some interesting papers on bracket, so-called bracket wormhole by, again, Maldacena, Gorbenko, and Yiming Chen. So yeah, I think all of these, if I have to guess what's the order, like 1 and 3 seem hard and probably involve some string theory, but 2 with this Jaffris Lamprou paper, maybe I don't know anything about cosmology really, and if people think about it, maybe there's progress to be made on number 2 and number 4. I think there was a question about the Trieste lectures. So it's not my Trieste lectures. Both Douglas Stanford and Ahmed Almehri gave lectures in Trieste. And in the PDF that I will send, I have one link to Douglas's lecture. And in that playlist, you can find the rest of the lectures as well. And I think Ahmed Almehri, in his lectures at ICTP, discussed this AHMST paper, like trying to get some more of this dynamics of the Schwartzian and so on and so forth. So I never even mentioned the Schwartzian, so I couldn't get into those details. But you can watch those lectures if you want to learn about that paper.
Can I ask a question? It's
yeah, please.
Recently there was a paper by, actually I don't know how recent, maybe in August or something, by Hong Liu and Shreya Vardhan.
Yeah.
And they have proposed an approximation scheme, and it's very beautiful in the sense that it's very naturally explains the Euclidean computations of
Mhm.
unitary of page curve.
Yeah.
However, the Lorentzian, the one that you are doing, Lorentzian, it doesn't seem like it's explaining that, and I'm not sure why.
Explaining, explaining the fact that the page curve comes down.
Yeah. So in fact, the
Yeah.
claim is that unitary. Yeah, exactly. So the claim is that it's guaranteed. The way the calculation is, and in fact, he shows how once you do replica using Schwinger-Keldysh contours and then do replica, and then you make an approximation, which has to do with, again, with this ZN replica symmetry. And then basically you are led to Euclidean calculation.
Yeah.
And there it's guaranteed that you have to have the page curve.
I think I know there are some papers that are published, and I think he gave a talk at this island hopping conference at CERN.
Yeah, I came to know about it from that talk only. Yeah.
Yeah. So I think what's happening in their papers is that there is a secret assumption of this Gaussian randomness. Like, you know, they have these operators that are growing in some sense, and they make some assumptions about these coefficients in the expansions of these operators of some kind of typicality and so on. So that assumption is essentially morally similar to assuming such a state and having theCij's be kind of random. So their derivation of the page curve is like the derivation I presented last time, is when you have, you know, 4 C's.
There's M and N, yeah.
Yeah, with this dimension M, and so there's a sum over, there's a sum over I from 1 to M, and a sum over J from 1 to N. And I think, sorry, I was calling this alpha. This was alpha, and there was things like C I alpha, C star J alpha, C J beta, C star J alpha. And there are 2 Wick contractions, right? That's like, if you have a Z2 symmetry, that's like the straight one and the Z2 partner.
Right.
And if you were computing trace row cubed, you would just have C and C star here, like more, so there are more Wick contractions. So what they're basically doing is a version of this calculation. And as we saw, this answer was M inverse plus N inverse. And this does explain why the curve goes down to 0 at the end. So I think that this is really what's going on behind the scenes in their paper.
Well, they do assume, in fact, that's the point they're making, is that if the state is, so I don't see where in their paper where this assumption comes in, but I'll look at it again.
No, it's definitely there. It's like they have this operator, it's growing, and they expand it as an identity plus some other thing. And yeah, there's a typicality assumption in that expansion of an operator into simple operators. It's clearer in their first paper, or first or the second paper. I haven't read the most recent one if it's out.
No, it's the second paper, I think. The one that that the talk was based upon, exactly that paper.
Yeah, but I definitely think that they do have some such typicality assumption.
Okay.
In the,
well, they do have what they call about equilibrated state, or maybe that's where it's creeping in. Okay.
Yeah, it's basically, it's something like this at the end of the day.
Okay. All right.
Yeah.
Thanks.
Yeah, please ask any question on the whole lectures or future directions.
Yeah, as I said, if you guys have any other questions, just also feel free to email me. I'll be happy to answer, and I will send these files to Jungi right after, maybe in the evening.
If there is no further question, let's thank Raghu for the wonderful 4 lectures.
Thank you very much.
Thanks also, guys, for being an amazing audience. Thank you. I had a lot of fun. Okay, bye.
Yeah, thank you very much. Yeah,
See you.
bye. Yeah,
Bye. Have
yeah,
fun.
see you.